In this video, I am going to explain magnetic field due to a current carrying solenoid. Solenoid is a long, closely wound coil. When there is an electric current, there will be a magnetic field. Direction of the magnetic field depends on the direction of the electric current. Direction of the current can either be in this direction or in this direction as shown by these arrows. Then direction of the magnetic field can be determined by right hand palm rule. So here direction of the current is along this direction as shown by the arrows. Hold the solenoid in your right hand such that fingers are in the direction of the current. Then the extended thumb will give you the direction of the magnetic field. So here this is the direction of the magnetic field. In this case, direction of the current is along this direction. So the magnetic field is that side. So one end of the coil will behave like a north pole, the other end a south pole. So in this case, when we look from this side, current is anti-clockwise. If the current is anti-clockwise, that end is north pole. When we look from this side, it will be clockwise, so that end is south pole. Similarly here, when we look from this side, current is clockwise, so that end is south pole, the other end is north pole. Next, let us see how to determine the magnitude of the magnetic field. Magnitude of the magnetic field can be determined by Ampere's circuital law. The line integral of the magnetic field over a closed loop is equal to mu0 times the net current. So that is the Ampere's circuital law. To apply the Ampere's circuital law, we are in need of a closed loop. So here we consider a closed loop. This coil can be represented like this. Here current is coming out. So that is shown by these dots. Here current is going into the board, that can be shown by this cross. Then here you consider a Amperian loop of length h. So that is arbitrary. We can take smaller or larger. So it is arbitrary. Or if you want, you can take this full. So now here there is a closed loop. Now this line integral b vector dot dl can be written as the sum of four integrals: a to b, b to c, then c to d, and d to a. So this closed a. So here again a to b, b vector dot dl plus b to c, b vector dot dl plus c to d, b vector dot dl plus d to a. We started from a, then end a. So it's a closed loop. Now this first, let us see the first integral, b vector dot dl vector. Here length and magnetic field. Here magnetic field, see when current is in this direction, magnetic field is that side. So here magnetic field that side, AB, both are in the same direction. So theta is 0. Here b vector dot dl dot product, b vector dot dl is b dl cos theta. Magnitude of b vector is b, magnitude of dl is dl, then cos theta. But in this case theta is 0. Cos 0 is 1. So this is b into dl. This integral will be 0 because here b to c, this length is perpendicular to the magnetic field. Magnetic field along this direction. So 90 degree cos 90, 0. So this will be 0. Then c to d, that is outside the coil. Outside the coil, magnetic field is almost negligible. It's 0. Only inside, magnetic field is inside is uniform. See, then again d to a. D to a. Again, this length is perpendicular to the magnetic field. So this integral dot product will be 0. Now magnetic field inside the coil is a constant. So this b can be taken outside. Then integral of dl, a to b. Then h. But this is arbitrary. So we can take this full length. So we length of this coil is L. So integral dl is, in this case it is H, but we can take this entire length of the coil. So entire length of the coil is L. So B into the integral dl, that is L. So B into L. So this is the Ambient Circuital Law. Here instead of this B vector dot dl we can write BL, then mu 0, then I enclosed, total current. So here current through each turn is I, then total number of turn is this capital N. In each turn there is a current of I, there is a current through each turn is I, then total number of turns N. So there is a total current, the current enclosed is, instead of this I enclosed, the total current we can write N I. Take this L to the other side, then N by L. So B is equal to mu 0 N by L. N by L, that is number of turns per unit length. Here total number of turns you are dividing by the length of the coil. So this is the number of turns per unit length. So for that we can write N. So B is equal to mu 0 Ni. So this is the expression for magnetic field due to a long current carrying solenoid. Magnetic field is given by B is equal to mu 0 Ni, where N is the number of turns per unit length and I is the current, and mu 0 permeability of free space.